Stop scrolling for a second. Tonight, when you look up at the moon, you're seeing something impossible. You are looking at the same face every human in history has ever seen. Every emperor, every explorer, every civilization. The exact same side. And here's the part that sounds suspicious. The moon is moving at nearly 3,700 kilometers per hour around Earth, yet it never turns its back on us. So what's going on? Is it stuck? Is it controlled? Is it just coincidence? Or is this one of the most precise gravitational relationships in our solar system? Let's break the illusion immediately. The moon does rotate. I know, that contradicts what most people believe. You've probably heard someone say, the moon doesn't spin. That sounds logical, because if it spun, we'd see different sides, right? Wrong. If the moon didn't rotate at all, we would see every part of it over the course of a month. The only reason we don't is because it rotates at the exact same speed that it orbits Earth. It takes about 27.3 days for the moon to orbit Earth once. And it takes about 27.3 days to complete one rotation on its axis. That synchronization is called tidal locking. And it's not an accident. Imagine walking in a circle around a friend while keeping your face pointed at them the entire time. To do that, you must slowly turn your body as you move. From your friend's perspective, they only ever see your face. From above, it's obvious you're rotating. That's exactly what the moon is doing. Now here's where it gets even more interesting. Billions of years ago, the moon wasn't like this. After it formed, most likely from debris created when a Mars-sized object collided with early Earth about 4.5 billion years ago, it was spinning much faster. But gravity doesn't just pull. It stretches. Earth's gravitational pull is stronger on the side of the moon closest to us and weaker on the far side. That difference creates tidal forces, which slightly elongate the moon. Over time, those forces caused internal friction inside the moon's interior. That friction acted like a brake. Gradually, over millions of years, the moon's rotation slowed down until it matched its orbital period. When those two numbers became equal, the system reached stability. And once locked, it stayed locked. Here's the twist. Tidal locking isn't rare. It's actually common. Many large moons in our solar system are tidally locked to their planets. Jupiter's major moons are locked. Saturn's Titan is locked. Pluto and its moon Charon are even mutually locked. They always show the same faces to each other. So the moon isn't unique. But our relationship with it is. Now let's interrupt something else you may believe. You've probably heard people talk about the dark side of the moon. That phrase is misleading. The far side of the moon is not permanently dark. It receives just as much sunlight as the near side. The only reason we call it dark is because we couldn't see it from Earth for most of human history. The first images of the far side weren't captured until 1959 by the Soviet spacecraft Luna 3. Think about that. For thousands of years, half of the moon was completely unknown to humanity. When those first blurry images came back, scientists noticed something surprising. The far side looks dramatically different. The near side, the side we see, is covered in large dark plains called Maria, formed by ancient volcanic lava flows billions of years ago. The far side, however, has far fewer Maria and many more craters. Why? Data from NASA's Grail mission, which mapped the moon's gravitational field in 2011 and 2012, suggests the moon's crust is thicker on the far side. That thicker crust made it harder for lava to reach the surface, which explains the visual difference. No mystery structures. No hidden civilizations. Just geology and gravity. But here's something even more fascinating. We say we only see one side of the moon. That's almost true, but not entirely. Because of small variations in the moon's orbit and tilt, a phenomenon called libration allows us to peek slightly around the edges over time. Thanks to libration, we can actually observe about 59% of the moon's surface from Earth. Still, 41% remained completely unseen until the space age. Now let's zoom out. The moon doesn't just passively orbit us. It actively shapes Earth. The moon's gravity pulls on our oceans, creating tides. But here's the detail most people miss. Earth rotates faster than the moon orbits us. Because of that, the tidal bulge in our oceans is slightly ahead of the moon. That forward bulge transfers energy to the moon, pushing it away from Earth. We've measured this precisely using laser reflectors left on the moon by Apollo astronauts. The result? The moon is moving away from Earth at about 3.8 centimeters per year. That's roughly the speed your fingernails grow. Billions of years ago, the moon was much closer. Tides were stronger. Earth spun faster. In fact, early in Earth's history, a single day lasted only about 5 to 6 hours. The moon has been slowing Earth down, and it has done something even more important. It stabilizes Earth's axial tilt. Without the moon's gravitational influence, Earth's tilt could wobble chaotically over long timescales. That would cause extreme climate shifts. Many scientists believe the moon's stabilizing effect has helped maintain relatively stable seasons, which may have played a role in the development of life. So when you look at the moon, you're not just seeing a rock in space. You're seeing a partner in Earth's long-term habitability. Now here's another pattern interrupt. Tidal locking doesn't just happen to moons. It likely happens to planets too. Many exoplanets discovered in the habitable zones of red dwarf stars are so close to their stars that they are probably tidally locked. That means one side permanently faces the star in endless daylight, while the other side remains in eternal night. Imagine living on such a world. One hemisphere blazing hot, the other frozen solid, and possibly a narrow twilight strip between them where temperatures might allow liquid water. Suddenly, our moon's situation feels less strange and more like a universal rule of gravity. But here's the philosophical twist. For all of human history, we've been watched by the same lunar face. Ancient civilizations mapped its patterns. Poets wrote about its shadows. Scientists studied its craters. And yet, for most of that time, we didn't know what was on the other side. It wasn't hidden by conspiracy. It was hidden by physics. The moon rotates. It orbits. And those two motions are locked in perfect synchrony because gravity demanded it. A cosmic coincidence? No. A predictable outcome of energy, friction, and time. So the next time someone says, the moon doesn't spin, you'll know better. It spins once every orbit. Perfectly timed. Locked in a gravitational dance that began billions of years ago and continues today. And here's one last mind-bending fact. In the extremely distant future, if the sun didn't interfere by evolving into a red giant, Earth and the moon could eventually become mutually tidally locked, showing the same faces to each other forever. Nothing in space is frozen in time. Everything evolves. The moon isn't stuck. It's synchronized. So tonight, when you see that familiar face in the sky, remember, you're looking at a precise gravitational balance that has shaped Earth's oceans, influenced its climate, and quietly supported life for billions of years. If this made you see the moon differently, follow for more deep dives that challenge what you think you know about the universe. And tell me this, if the moon were suddenly unlocked and we could see a completely different face tomorrow night, how do you think humanity would react?